Hello. Thank you very much to all of the organizers of this conference. It's really fantastic to be able to participate. Big thanks to Naira for asking me to speak today. I'm going to talk to you all today about a ubiquitous type of geometric object, something I've been thinking about for quite a few years now, called minimal surfaces. Hopefully, I can give you just enough of the story of their development, what they are, what they're all about, that I can give you, roughly speaking, a little bit of a picture of where my research that I've thought about for the last few years actually fits into this story. Okay, so we're going to start with an almost ludicrously basic geometric observation, that a straight line is the shortest path between 2 points. Okay. So here's my straight line segment from A to B. Of course, I could, in theory, extend the line off that side and extend the line off that side and forget about A and B, and I'd have what you'd call a straight line, but it wouldn't really be the shortest path between anything or anything. There'd be no endpoints. However, anytime I cut a little portion out, what I would see is the answer to the question, what is the shortest path between those two endpoints? Okay. So let's do a little thought experiment now. Suppose I'm here. We'll kind of act out this abstract geometric observation in real life. So here I am on these salt plains, which are incredibly flat, and they go for miles, very, very flat. And suppose I do indeed look at a point a few meters ahead of me and take the shortest path between where I am and that point. So I walk in a straight line from where I am to the point just a few meters ahead of me. And suppose I keep doing this. When I arrive there, I look again a little bit further ahead, and I take the shortest path between where I am and the next point. I'm walking in what seems to me to be a straight line. And at any given time, I'm taking the shortest path between where I am and the point just a few meters in front of me. Of course, though, at some point in human civilization, I mean, it's a non-trivial fact, but at some point we figured out, despite how flat it looks in pictures like that, the Earth is round. And this is a remarkable fact, really. And actually, this by itself contains the seed of, perhaps some of the foundational ideas in modern geometry, that a space can seem very flat, like in the previous picture, but when you zoom out and look at the big picture, it's curved. So we're going from, as is often the case in mathematics, the very, very basic shortest path between 2 points is a straight line, and very, very quickly we're touching on some actually much deeper ideas. So if I continue walking in this fashion for a very, very long time, in theory, I go all the way around and I arrive at the spot just a few meters behind me. So I've now by no means taken the shortest path between my original starting point and my final endpoint. The shortest path would be to turn around and just go a few meters backwards. Okay. But at any given time, I was taking the shortest path between where I was and where I was going, a few meters away in front of me. So here's a nice summary sentence. Taking the shortest path locally does not result in the shortest route globally. Of course, if I really do continue, I close back up the circle and I would trace out what we call a great circle around the Earth. And it's this object I want to talk about just a little bit more. I think I'll sort of say two things. The first is that if we take a portion of this great circle that's not too large, then we really do see the shortest path between the endpoints of that portion. Okay. So just like the abstract actual straight line, I can say that it's answering the question, what is the shortest path on the surface of the Earth between A and B? Answer, it's that portion of a great circle that connects A and B. But when I zoom out and look at the full great circle, it's not the shortest path between anything or anything. There aren't any endpoints. It's not minimizing length in some way. It just is this complete object. And moreover, the line segment by itself isn't very interesting geometrically. It really feels like it's a fragment. Whereas the great circle itself is not super interesting, but there's some beauty and symmetry to it. It's a nice perfect circle and it sort of splits the sphere in half nicely. And there's something satisfying about it. Okay. So these things are going to act as an analogy, really, for the next part of the talk, but they're going to be important ideas to bear in mind. Okay. So what we'll do now is I guess another kind of thought experiment. It'll be slightly more sophisticated than walking in a straight line. It's a classic experiment used in explaining minimal surfaces, which involves soap. So I want you to imagine you've got a wire loop and it's flexible, so you can kind of deform this, bend this loop a little bit. So it's not a perfect circle, sort of a bent loop, and you dip it in your soap solution and you lift it back out. And a soap film has formed across that loop, spanning that boundary. And the remarkable thing here is that purely through physical principles, the soap film is trying to minimize its own surface area. Okay. So you can see at the top there, from length minimizing paths to area minimizing surfaces. That's the analogy. So let's try and say that a different way. What does this mean to be an area minimizing surface when you've got this boundary loop? So you can think that loop creates a hole, and there are lots of different surfaces, lots of possible different ways you can fill in that hole with a surface. Okay, well, what's the one with smallest area? What's the one with smallest surface area? The soap film is approximating that surface, the one with smallest surface area. Okay, so as I say, this is a classic experiment used to demonstrate or motivate minimal surfaces. The historical narrative is that back in the 18th century, the mathematical abstract version of this problem was first asked. In fact, at some point a few years ago, I found the transcripts, you can maybe find them online somewhere, of these letters. There was letters written by Lagrange to Euler. And this was just before they developed the calculus of variations. So this problem was a real prototype problem in the development of the calculus of variations. Okay. It later became known as Plateau's problem. But Plateau is actually much later than Euler and Lagrange, who first discussed this problem. So roughly speaking, Lagrange asks this to Euler. He says, okay, suppose you're given this boundary loop. I've called it gamma. So gamma is the blue wire in the previous slide. Okay. So you start somewhere, you draw this loop in three-dimensional space, you end up where you started. That's your boundary loop. So fix that gamma. Is there a surface, sigma, with smallest surface area among all the possible different surfaces that have gamma as the boundary? Okay. You have to say, is there? It's not even clear there is one with smallest surface area. So is there one? And if there is, what does it look like? What can you say about it? Right, so that turned out to be actually a very difficult problem. And this is a great example in mathematics of, I mean, as I say, there are these letters, apparently you can read them. They're sort of discussing things, innocent questions come up, and occasionally you hit upon an innocent question, which then gives birth to lots of development of mathematics and some very deep ideas. This is a great example of that. So, well, how about this question? Turns out to be a very important one. At the time, they didn't make any progress with it, basically. They sort of said, wow, that's interesting, too hard, don't know. What they were able to do was produce an equation which was a necessary condition for sigma. So I'm going to explain that just coming up. So this equation is what later was called the Euler-Lagrange equation for the problem. So in this context, it's called the minimal surface equation. Okay. And this is the delicate point. It's a necessary condition. So it's of the following form. You fixed your boundary curve, the blue wire from the previous slide. That's a fixed thing. And the condition is such that if surface sigma solves the problem, is the surface with smallest surface area, then it solves the minimal surface equation. Okay, so that one-way implication is it's a necessary condition, but not a sufficient condition. The implication doesn't actually go the other way when you talk about the minimal surface equation by itself. The minimal surface equation doesn't mention the boundary curve. And I'll explain a little bit about what the minimal surface equation is actually like in a couple of slides' time. But the analogy to bear in mind, which is just straight out of basic calculus, is this one. F primed of x equals 0 is a necessary condition for x to be a minimum of f. And that is a completely appropriate analogy, because what you're doing is finding a minimum of a function. So the analogy works in that the different values of this little x are the different possible surfaces that have sigma as the boundary. The different ways of filling in the hole with a surface are the different values of little x. And the function f returns the area of the surface. So you're trying to find a minimum of this function f, and a necessary condition is the derivative has to be 0 at a minimum. And that's what an Euler-Lagrange equation is. So nowadays, this would be sort of undergraduate mathematics, like you take some course in sort of applied methods, something like that, where they talk about generally finding out Euler-Lagrange equations for different problems. So the inquiry sort of segues a little bit because the original plateaus problem is somehow too difficult. The inquiry segues to, well, can we find anything, any surfaces that satisfy the necessary condition? Whether or not they turn out to be true minimizers for some actual plateau problem that we're trying to solve, we've sort of forgotten about that. And so say, well, okay, we've got this necessary condition. It's very interesting. Can we find any surfaces that might satisfy this condition? So at the time, I think they found one, which was the completely flat two-dimensional plane. Okay. And then in the 50, nearly 60 years that followed, 2 more minimal surfaces were discovered. It's almost surprising the subject survived given such a slow rate of progress, but what it meant was that subsequently theorems that produced new minimal surfaces or that constructed new minimal surfaces, existence theorems for minimal surfaces, they were always quite well regarded. It was always seen as quite difficult to do and quite interesting when you did it. Okay, so the three that were discovered are sort of the three classical minimal surfaces, and I'll tell you what the other two that aren't just completely flat plane are, and I'll also give you slightly more explanation as to what this minimal surface equation is really saying. Okay, so the second classical minimal surface is the catenoid. So here are two pictures of a catenoid, and then you can see it actually formed out of soap film in the bottom two pictures. In cylindrical polar coordinates is defined by that equation, z is equal to, so that's inverse of hyperbolic cosine of the radius r, for r greater than or equal to 1. For very large values of r, if you look at picture B, so that's kind of zoomed out. So for very large values of r, inverse cosh is a bit like log r. So the height of the surface above the z equals 0 plane is about logarithm of r. So it doesn't actually flatten out and tend to some plane like that. It is actually increasing and increasing and increasing and tending to infinity in that direction, but very, very slowly. So when you zoom out homothetically, you'll see the two sheets get closer like that. So this is a nice, beautiful shape. To help explain the minimal surface equation just a little bit more, let's look at picture C. That soap film where you can see the middle neck of the catenoid very well in profile. So look at the edge of that where you see it kind of bending inwards like this. And we'll look at that point right in the middle of that bend, right in the middle of that catenoidal neck. So roughly speaking, there are sort of two main directions in which you can think about the way the surface is curving. There's the vertical direction, where it really is curving inwards like this. Then there's what's going on in the horizontal direction, where it's curving somehow in the opposite sense. Okay, so in the vertical direction, it's curving one way, and somehow in the horizontal direction, it's curving the other way. The other way. These two curvatures being equal in magnitude, but somehow having the opposite sense, is precisely the minimal surface equation. A minimal surface is a surface that satisfies that at every point. That's kind of hard to see because I haven't really given you definitions of what those two main curvatures are. But interestingly, if we go back, it's actually illustrated very well by this photograph. It really is almost perfectly saddle-shaped in the middle. You've sort of got that roughly left-right direction in which it's curving like that, and roughly the forward-back direction which is curving the opposite way. So it looks neither sort of completely, concave or completely convex or anything. It's sort of one direction curving up, down, and the other direction curving sort of down, up. So minimal surfaces have that kind of saddle type curvature at every point on them. Okay, so I'll go to the third classical minimal surface now. That's the helicoid. This is another very beautiful shape. It's essentially the shape of a spiral staircase. And there it is also made out of soap film, which is quite remarkable. Of course, you have to cheat a little bit because we have to cheat a little bit in the picture as well. So the picture is a helicoid, but then cut off in a cylinder, and obviously cut off in the vertical direction as well. So you're seeing this like little portion of a helicoid that's been cut out. And the same with the soap film. To get that to work, you have to connect it up in the right way, and you have to have a rod going all the way through the middle. But it's still quite remarkable that the soap has actually produced that. So we can explain these parametric equations a little bit. Imagine fixing theta equal to 0. Okay. So z equals theta. So what that means is we're kind of looking at the surface in the xy plane. Okay, so what is the intersection of the surface with this horizontal z equals 0 plane? Well, then what you see is just a line. Okay. You just see a single line. So it would be the, I guess you'd see the x-axis or something. And then imagine increasing theta at sort of constant speed. Okay. So what happens is this line increases its z coordinate at a constant speed because z equals theta. But when you just look at the equations in x and y, what happens is the angle of the line in the xy plane changes at a constant speed. So the line moves up at a constant speed and rotates that way at a constant speed. So as you move this line up and rotate it, it sweeps out the helicoid. Okay. One more remark I'll make about these surfaces, if you have any interest in the topology, and I won't say any definitions about topology, but interestingly, the catenoid is an annulus, so that sort of doesn't just look like it has a hole in it, it really does topologically include a hole. But the helicoid is a plane. It's a vertical plane that has then been sort of corkscrewed all the way down it. So it's topologically trivial. Okay. So no talk on minimal surfaces sort of complete without some of these pictures of classical minimal surfaces. But let's go back a little bit to the original problem, Plateau's problem. Because like I said, the inquiry sort of segued out of solving Plateau's problem for many years, whilst people looked for examples of two-dimensional minimal surfaces in R3 that weren't to do with boundaries or anything. The connection with some of the earlier part of this talk, I think, was only completely understood a little while later, which is that actually if you take a sufficiently small portion of one of these minimal surfaces, then the picture you see is of an area minimizing surface. So that's the analogy. So let me go through this one more way. If I cut out a little sufficiently small piece of my catenoid, then where I've made the cut, I produce a boundary. And filling in that boundary is a piece of the surface. Now, although the whole catenoid isn't sort of minimizing area in any meaningful way, where I've made that cut, the piece of the catenoid is the surface of smallest area that has the boundary I've produced by making the cut. We won't need to kind of go into that anymore, but it's completely analogous to the portion of the great circle on the surface of the Earth that's connecting A and B, and how the circle itself was this complete beautiful object, just like the catenoid is. But when you take small portions of it, there's a solution to a minimization problem. But Plato's problem goes the other way. It gives you the boundary and says, well, can you find the area minimizing surface? So what we've seen so far is how that led to the development of this classical minimal surface theory, catenoids, helicoids, looking for these beautiful complete pictures in three-dimensional space. And it's a big area of mathematics still today, and actually, in my opinion, a very difficult area to make progress in. So the dichotomy I'm presenting here is nowhere near as neat as I'm going to make it seem, but there's a parallel development that Plato's problem is responsible for largely, and that's the development of geometric measure theory. So whereas the classical minimal surface is sort of a segue out of the original Plato's problem, geometric measure theory really came about when people were directly trying to solve Plato's problem. It came about because it was realized you more or less have to deal with singularities. Okay, so this is kind of where my personal research interest in this whole thing mostly lies. It was realized that, well, there are sort of two ways I can motivate this. Okay, I'll first say what a singularity is, and then I'll give you this. So any point on a surface that is not a single nice smooth sheet, we're going to call a singularity. And that could be any point where you see a self-intersection of the surface, or a hard angle, or somehow where the surface is badly contorted or wrinkled or sort of pinched. It's hard to sort of imagine this happening. But there are two ways this was arising. One was the best ideas and methods people had for solving Plato's problem seemed to have to allow for the possibility that there were singularities on these surfaces and that the solution wasn't just a sort of single smooth surface. So there's sort of, it was arising kind of in the mathematical methods. They sort of said, well, I can't make the mathematics work unless I allow for the possibility that the surface intersects itself or something. But also, it's very easy to produce these things with soap film. And so if the soap films are kind of telling us as much as we think they might, then you have to be prepared to allow for singularities. So here, the red wire is a boundary that's not terribly complicated. It's a bit more complicated than the blue wire we saw earlier. But the soap film has formed, along a line in the middle, this hard angle. We call it a triple junction singularity because you've got three sheets, each of which by itself is a nice smooth sheet. But where they meet, it's not a single nice smooth sheet. It's a hard angle where three are meeting along a boundary. So this seemed unavoidable. And a lot of mathematics had to be developed to somehow handle this in sufficient generality. It's sort of easy to point at one singularity and be like, well, that looks quite simple. I could just sort of, in an ad hoc way, add a description of that into my mathematics. I could sort of write down three sheets, they meet at 120-degree angles, like I've shown in picture C. That doesn't seem too complicated. But the point is more that you don't know what they're going to look like. So soap films actually produce another more complicated type of singularity that actually a lot of people would never have really seen or thought about, which is a tetrahedral type singularity. So already you think, oh, that looks a bit more complicated. And it should give you a bit of a hint that you can't be sure you've found all possible ways in which you could have that sort of complicated picture of sheets meeting along lines at different angles. How can you classify these in order to have a sort of complete theory? So in this tetrahedral singularity, there's actually 6 sheets that meet at that middle point. Along each line connecting a vertex of the tetrahedron to the middle, you see triple junction singularities. Okay, so the previous type of singularity is also appearing in this picture, but at the middle of this picture is a new type of singularity. So there's a whole nother field of mathematics that sort of comes out of this, developing these tools to handle these kinds of things in increasing generality. So I'll just give you a couple of little remarks about a success story involving these things. So much later than the other dates I've mentioned, in the 1970s, Almgren, one of the pioneers of the modern geometric measure theory, and Gene Taylor produced a lot of work in geometric measure theory, which actually resulted in a classification of the types of singularities that occur in a particular formalization of soap films. Okay, so you use geometric measure theory to produce a formalization of soap films in the mathematical theory. Then they use geometric measure theory to prove the only singularities you see are the ones I've just mentioned, triple junctions and tetrahedral types. And there are many, many more questions in this area. Broadly speaking, sort of regularity theory is what it might be known as, the regularity theory of minimal surfaces. And that's an area which I've spent a lot of time thinking about over the last 5 years or more at the moment. Okay, I'll stop here. Thank you very much for listening. I look forward to taking any questions from you live if you have them. Okay, thank you.